Welcome everybody to session number 10. This time we are on the frontier. We're going to bring everything together to be able to look at something that's truly state of the art and really be able to understand most, if not all of it intuitively, even if not down into every aspect of the code. But first, of course, you guys know we're on a mission to create the world's leading community for people that want to build, ship, and share production LLM applications. Who's been building and shipping and sharing this week? I don't think anybody's going to be surprised to see Nilay and Sahar holding it down in the channel. Love that you guys have continued to do this week after week. I can't wait to see what is in store for everybody that's been getting after it in 2025. Last one of the year, by the way. Come join us next Monday. Then we're going to take a week off. If you have stuff you want to get done next week, I certainly do. Stuff that just doesn't fit in to the rest of the daily grind of, doing this and doing that, doing the day job and doing all of the other things associated with family and life. If you have special projects, it's a great week to try to crush them. Join us on Monday. I'll be in there and I'll be telling you guys what I'll be working on as well. And here we are, everybody. We have taken a journey together over the last 6 weeks to find out this diagram is indeed mid. Well, what is on the frontier? Well, we've got all the pieces in place to be able to kind of understand and grok what's on the frontier, to be able to read any research paper that comes across our desk, to be able to dig in to any piece of vocabulary that might be new and might be fit into a transformer architecture context. Today, with that in mind, we're going to take a journey through distillation. And we're going to think about how we can actually do this kind of thing today if we want to. We're going to actually dig in from whence we came, talk about Supernova, dig into the technical training report they released, and be able to read it with fresh eyes. We're going to talk about continued pre-training. We're going to talk about what is on the edge beyond that. And we're going to play some games and have some fun graduating from LLM Engineering Cohort 3. So we're going to walk through each of these. We're going to spend quite a bit of time on distillation and continued pre-training. We're going to talk about the learning path we've taken and that we would advise others to take, and that you should go evangelize out there wherever you go next. And then we'll have some fun before we talk frontiers and have a little celebration at the end of our final 2 hours together. Distillation. This one's pretty easy. We just make big models smaller. All right, that's it. Okay, we're done. You probably have some intuition around this already. And you might be right. Let's take a walk down days past lane. I'm not sure if I remember any of this, although most of us were certainly alive in 2006 when the original knowledge distillation paper came out called Model Compression. We present a method for compressing large, complex ensembles into smaller, faster models, usually without significant loss in performance. And this idea is the big idea. Take a big old model and create a smaller, faster, more compact, more easy to use model. We're approximating what the big model can do. If you have an optimization background, you might call this a surrogate model. This is something that has been happening forever in these kinds of spaces. And it's something that is always going to be important as long as we have more compute that we can use. We are going to have bigger models, and we're going to want to use bigger model power on small devices. We're going to want to use them on smaller hardware. We're going to want small businesses to get access to them. This is a sort of fundamental problem that isn't going away. And the way we kind of solve this problem, I want to introduce a piece of terminology that wasn't in the paper. I want to introduce this idea that the fast compact model is the student and a slower, larger model that is the teacher. Back to the paper. We read that the function learned by the higher performing model is available and can be used to label large amounts of pseudo data. Okay, all right. Labeling pseudo data. Nice. The fast compact model can be trained on this pseudo data. And if it is, it's not going to really overfit. It's not going to it's going to approximate well. And it's going to basically approximate whatever this sort of function, the sort of objective function, the sort of cost function learned by the high performance model. And again, they're belaboring the point here. This allows a slow, complex model to be compressed into a fast model, such as a neural net. 06. That's pretty hype. An important question is, how do we get pseudo data? In some domains, large amounts of unlabeled data is easy to collect. Indeed. Excellent foreshadowing here. How old was the internet in 06, really, for consumers? And then there's a whole lot of additional words here. I've highlighted the word synthetic here a bunch of times. The idea is that if you're not in a domain like that, which of course large language models typically are, you might have a little bit more of a problem. You need a minimum number of samples. So fast forward 9 years. 9 years. And this original gangster, Mr. Hinton, Dr. Hinton, writes a paper March 2015 called Distilling the Knowledge in a Neural Network. We achieved surprising results on MNIST, what a classic, and we show that we can significantly improve the acoustic model of a heavily used commercial system by distilling the knowledge in an ensemble of models into a single model. Now let's read what Hinton writes. See if we can track it now. Knowing what we know, I think we can, but it's tough. Neural networks typically produce class probabilities by using a softmax. Okay, all right, Jeff. Distillation, this is like the original sort of thing. That converts the logit computed for each class into a probability by comparing with the other logits. Okay, so far so good. Where T is the temperature, using a higher value for T produces a softer probability distribution over classes. We're sort of heating it up, right? The temperature. In the simplest form of distillation, knowledge is transferred to the distilled model by training it on a transfer set and using a soft target distribution for each case in the transfer set that is produced by using the cumbersome model with a high temperature in its softmax. Immediately, I'm off way in left field. Was that sentence really necessary, Jeff? Hey, you know what? That's academic papers for you. I got a question here, Wiz. I want to bring you in on this. What is a soft target distribution here? What are we talking about, really?
Well, just not a hard target, right? So the excuse me, sorry. Typically, when we look at the target distribution for a traditional, unsupervised or self-supervised learning, pre-training, SFT, we have like a correct logit, right? That's the one that we want to select versus these distillation problems where we actually have, instead of just like basically one token is correct in the vocabulary, so the distribution just looks like one hot encoded vector basically. We can have these softer, actual produced by a model distributions which contain a range of probabilities.
So when we soften it up, it doesn't have to be like exactly correct. It sort of can be approximately correct, something like this.
It's more like well, yeah, so we still want it to be exactly the same. We'd love if the distributions that are produced were exactly the same, but the nice thing about it is that we don't have one response, right? We're not training the model to be good at just producing that token next. We're having the model be able to produce a distribution that looks the same as the teacher model. And the reason that's so beneficial is, we've learned about things like decoding strategies, right? These decoding strategies are influenced by the actual underlying distribution that's produced from our model. And so you can think of it as, if we learn that soft distribution, though we still need to be bang on the money. That's the desire. We're going to be able to learn not just what the next token is, but what a likely set of next tokens are, and that's kind of what gives us this ability to learn, our target very well. So the idea is that the LLM doesn't produce a one hot encoded vector, right? Though it could with greedy sampling.
Hmm.
We instead have this nice, beautiful, like, well, cat might be next, or I don't know, rat's kind of similar, and dog's kind of similar, and learning that more rich representation of quote unquote what comes next is how we can do this whole distillation thing. Yeah.
Nice, nice.
Yeah. Yeah.
All right, excellent. Thank you for that helpful explanation on this soft target distribution idea. So here we can see, words that we're comfortable with now that are firmly in our wheelhouse. The first objective function, the first thing we want to optimize, this idea of what number are we looking at so we can actually get better, is the cross entropy with the soft targets. All right. The second objective function, the cross entropy with the correct labels. Okay, all right. So we can kind of see what's going on here. We can kind of intuit what's going on here in this paper originally about distillation. And interestingly, in the abstract, Jeff also mentions, hey, unlike a mixture of experts, put a pin in this one for a little bit later, these specialist models can be trained rapidly and in parallel. Fast forward 4 years. And here's our good friend BERT. But this is actually the DistillBERT paper. You may have heard of DistillBERT before. It's a distilled version of BERT. That's literally the title of the paper here. What a classic. Smaller, faster, cheaper. We propose a method to pre-train a smaller general purpose language representation model. Very fancy words here, which is called DistillBERT, which can then be fine-tuned with good performance, as it has been many, many times. Now, one of the favorite pieces from this paper for me is, look at this beauty right here. Look at these insane parameter counts. And then NVIDIA is just crushing it when this paper comes out with this massive 8.3 billion Megatron LM. Wow, what an incredibly huge model that is. And they're like, hey, it's too big. Nobody's going to be able to do this 8 billion parameter model thing. Am I right? This game is never ending. Hence why we need things like distillation. If we zoom in, actually, what they tell us is to really do this thing, they introduced a triple loss naturally, combining language modeling, distillation, and cosine distance losses. Of course they did, because, well, everything is loss, as we've continued to see throughout this entire journey together. So DistillBERT is the same as BERT, but smaller. Finally, Hugging Face comes in and they write some words that we can actually understand. They're not in this research jargon. It was trained by distillation. And specifically, the way they talk about it is it's just being trained to predict the same probabilities as the larger model, hence the softmax of the logits. So the actual objective is a combination of these losses. And as you get more advanced, you'll see these combined loss functions and they'll have different contributions from different pieces of the puzzle, finding the same probabilities as the teacher model, predicting masked tokens correctly, and using this cosine similarity between the hidden states of the student and the teacher model. That's an interesting new term there. Let's fast forward now 5 more years to today. Supernova came out. This is what we talked about in session 1, the best 70 billion model on the market, distilled from Llama 3.1 405B Instruct. Distilled. How was it distilled exactly? Well, the distillation here can be done with the distill kit from Arcee. It can be done either logit based or hidden states based. Now, the first thing to know about the difference between these two is logit based, straight from the docs here, model can be the same architecture. Generally, we're using models with, you know, we're getting more and more, as we talked about, emerging towards a place where we can kind of do stuff with models of slightly different architectures or even wildly different architectures. And the hidden states based distillation, the models can actually be different architectures. Now, the constraint here between logit based or hidden states based is actually that the tokenizers really need to be the same. And when we think about like what's a tokenizer, we can actually build this up from first principles real quick. We know logits are the raw and normalized scores for each token in the vocab. And we've talked many, many times about softmax and how those are the normalized probabilities. Well, the tokenizer is simply the logit index. That's it. And so we need that same logit index, you know, if we're going to do like logit-based distillation. And we're going to have a teacher model. It's going to be the big model. We're going to have a student model. We're going to have some data. The teacher model is going to label it. The student model is going to be like, oh, and, you know, we can continue on. Now, the hidden states-based sort of approach here uses actually intermediate layer representations. That makes it a little more compatible across architectures. So I've got a few questions here that I want to kind of discuss with, and maybe we can touch on a few in the chat here as well. But okay, so first of all, is distillation fine-tuning or not? What's your hot take on this?
I mean, no, but yeah.
I mean, I say yes, you know.
It's literally training as opposed to fine-tuning, because we're starting with a we're not fine-tuning an existing model, right? So there isn't a model that is good at a thing that we then fine-tune to be better at some other thing in most cases of distillation. So I would say, you know, the answer should be no, but also it's kind of yes, because we're trying to get these very like granular small updates to the weights. We're not like learning the whole corpus, but the literal, I think by the literal definition, we just have to call it training, and then deal with whatever else.
Okay. Question in the chat here from Seth. Why do the teacher and student models need the same architecture for logit based? Wouldn't they just need to have the same sized logit vectors?
No. So essentially what we want to do is we want to recreate the internal state or the hidden states as closely as we can in the small model. So it needs to have the same transforms as it flows through the network. So we can't use a different architecture for logit based. Essentially, if we did that, the logits would mean something else, you know, then like to that model than they would to the other model.
And just to quickly kind of touch on this, is this teacher-student approach something that we should have, you know, as AI engineers in our back pocket today, heading into 2025? Is this something that, you feel is important for people to know, to understand how to do, to be able to actually implement?
Yeah. Yes and no. So this is another one of these things where basically other people are probably going to do this for you. Like bigger companies. I know a certain company, whose name rhymes with Schmividia, just released some distilled models that are quite performant. But it's one of these things where if you have a target model that you're trying to make more optimal, right? If your job is to, instead of like construct a model or fine tune a model, if your job is to make model go BERT faster, then distillation is, especially as we get better at it, just like a really easy way to do that. Especially with some of the new techniques that we see coming out that are, I'm sure, going to make their way into some technology we'll talk about in a little bit. But we can be very flexible about how we approach distillation. So it's a good tool in the back pocket if you're looking for optimization. Otherwise, these distilled models are just kind of going to be done for you, a la your Llama 3.1s, right, or your Quens, where we're using these big pre-training shops, artifacts.
Yeah,
So
like or DistillBERT, right? I mean, there'll be common ones that people pick up and
yeah.
use, right? So Martin asks, can you pre-distill with pre-training instead of having to follow up with distillation after a model has been trained?
Yeah, absolutely. That's what you're going to do most of the time, in fact, right? So we're gonna start with randomly initialized weights, and then we're gonna learn that probability distribution. So that's most of the time what we're gonna do for distillation. It is not dissimilar to pre-training, right? We're At the end of the day, we're just trying to create a model that it produces the other model's outputs really well. And the idea is that should mean it's as good as the other model most of the time, right? So, but yes, you can start from blank. You can start with like halfway there. You can start with a smaller version of the parent model, right? But sky's the limit for distillation.
Nice, nice. Okay, excellent. Now, one last kind of hook here, though, on synthetic data generation. It feels like we're kind of just generating some synthetic data here and using it for training in the end. That's kind of how it feels to me. Is that what's really going on here?
Uh, so yes, in SDG based distillation techniques for sure. So
Ooh.
when we're using distillation, as in we're creating a training corpus with a parent model, right, or a teacher model, then yes, it's literally just SDG, straight up. That's it. In fact, more traditional distillation is a little bit different, right? But there is lots of distillation techniques which we see all over the place, including in again NVIDIA's newest kind of distilled model releases that basically just say, I mean, well, we can create a great training corpus that we can just use to train our next model, and we can create it in such a way that it comes out of the box high quality. High quality data is more efficient, so you can train a smaller model faster with less data, et cetera, et cetera. So yes, literally, it can just be SDG. That could be your entire distillation strategy. Yeah.
Nice, nice. Okay, all right. Thanks, Wiz. And so now, finally, we can look at a process like this and understand it. The distillation, the fine-tuning, the alignment, the merging. Let's read together the technical report that they provided. It's very interesting now that we can pay attention to the details. The distillation process starts with the distillation of Llama 3.1405b instruct using DistillKit. Now, initial attempts here to distill the model in real time proved computationally prohibitive. Specifically, it was just too much for the stack that the company Arcee had access to. To overcome this, they switched to a method of logits extraction applied to a carefully curated data set. Interesting. Very interesting indeed. 500 million tokens here is what we're talking about. 2.9 petabytes. And this idea of taking the logits and then compressing them, 2.9 petabytes compressed to 50 gigs, was pivotal and was kind of new enough that they're thinking about writing a paper on it. But it's a competitive market out there, and research is done in companies now just as it's done in academic institutions, because you need those GPUs. They might not release it, but they might. Stay tuned. And then after the distillation, or I should say the distillation took 5 days, 32 H100s. They got a pretty fat stack there, still not enough to like actually distill that 405B. This is like the whole, you're going to want companies to do this for you. It's typically not something that you'll probably be doing. Now, in parallel, they took separate versions of Llama 3.1 70B, and they fine-tuned it using their custom fine-tuning approach. We'll mention it later. It's called Spectrum, and it's a little bit different than LoRa. It uses a slightly different approach. It uses a signal-to-noise ratio approach, and it's potentially better at distributed training versus LoRa being kind of the gold standard for non-distributed training. This model was trained on a data set that they created using their synthetic data generation evolution pipeline, 76,000 samples, both proprietary and openly available data was used to start this thing. And they used a quantized version using GPTQ. If you want to know about quantization and different techniques for that, as well as SDG is something that we cover in the next course. The completions for these instructions were generated by a mixture of large models. So they gave it instructions, and then they said, yo, big guy, can you complete these? This wasn't even in the distillation process. This was in the next fine-tuning process. So you guys tracking? Let's keep going. The phase of training at that point was one where they wanted to checkpoint. And they wanted to do this checkpoint merging every half of an epoch of the 3 epochs that they did the training. They employed a now proprietary merging technique. Of course, we looked at merge kit, but is that really where their secret sauce is? They go deeper naturally. And I'm pretty sure they're thinking about a paper there too, but are they really going to publish it? I suppose we'll find out in time. In the end, there was DPO and there was a final merge. We know DPO. We know QLoRa. And this was done on a single 8 by H100 node. That's 8 H100s, not 32. Maybe we can get access to nodes like this size to do things like alignment, when we're building these types of models and solutions out there in industry. The DPO also used this checkpoint merging strategy. The final version was produced by merging the checkpoints and then merging the distilled version. And then they did some additional stuff and then they decided to throw it out. Now, what were the results? Well, the results were like, hey, this was dope. Distillation, checkpoint merging, instruction tuning, using their, SDG, their fine tuning, their merging, but it didn't do better on every single benchmark. It did better on most benchmarks. GPQA is the graduate level Google proof QA benchmark. It didn't do better than out of the box or any other 7dB model. And Muser here, the multi-step soft reasoning, it also didn't super crush. We'll come back to reasoning models. So now we can kind of look at this landscape of complexity and we can start to break it down into first principles, knowing what we know about LLM engineering. And this leads us to the last thing that we want to add to your core stack of things that you should know. And we're going to start doing a little dance because this paper does it as well. April 2020. It's called Don't Stop Pre-Training. Turns out a second phase of pre-training in domain called domain adaptive pre-training, can lead to performance gains. But that's not all. Adapting to a specific task instead of a specific domain can also improve performance, even after domain adaptive pre-training. This feels a lot like fine-tuning. But we go further, adapting to a task corpus, augmented using simple data selection strategies. If you don't have them GPUs to keep on pre-training, might also work. So there's just a lot of ways to keep pre-training. We did an event recently with one of our friends from Unsloth. Daniel and his brother over there are crushing it, and you should definitely check out their stuff. They are doing a ton of micro optimizations of making stuff run faster and being able to do stuff faster, like fine tuning and pre-training and doing things like continued pre-training. And they looked at a paper called LoRa Learns Less and Forgets Less. This was kind of a cool thing where they kind of looked deeply at LoRa. This is from 2024 and compared the performance of LoRa and full fine-tuning on 2 target domains by considering both an instruction tuning data set, 100K, it's 100K, and a continued pre-training, more like 20 billion tokens instead of these 100K prompt response pairs. That's kind of the way we can think about this. We're using this unsupervised pre-training approach versus this supervised fine-tuning. And they got slightly better results. It's pretty dope. And you should definitely check out what they're doing. It's pretty cool. So Wiz, I want to talk a little bit about this now with you here. This is the figure, and it's very meta from this paper. We have this original language model domain, and then we have sort of this, this sort of subset of that original language model domain that we want to really, crush and be good at. And it's not the whole thing, but it's part of it. And there are strategies to get better at it simply by doing more unsupervised pre-training, to focus in on a specific domain. We talked kind of about focusing in on a specific type of language when we talked about fine-tuning, to focus in on a specific task. We talked about that during fine-tuning. And then there's sort of this final thing in the end here where we kind of have the domain adapted, the task adapted, both, and then we've got this KNN task adapt. And like, what's the big takeaway from this for you when we think about pre-training and continuing to do more and more of it? And sort of, where do we sit today? This is obviously from 2020. People like Daniel are doing it. What should we really be taking away from continued pre-training, and should it be a tool in our toolbox?
Definitely, it should be a tool in your toolbox if you are in a big shop with lots of GPUs. The moment that we hear the word pre-training, right, we know that it's going to be expensive computationally. But yeah, I mean, think of it this way, right? If I taught you, Greg, one thing about, say, one particular topic, let's say like cheeses of the world, right? And then you got really good at knowing about cheeses of the world. You know what I mean? But you have some background knowledge and a bunch of other stuff, you could still talk about things like law. You could still talk about things like, whatever else, but you wouldn't be great at them. And so what we need, and like fine tuning your cheese knowledge, right, isn't going to get you super close to law. Even if we fine tune a lot, right? Like you're over here in cheese land.
Yeah,
Not a
but
lot
that's
of
the box.
transferable knowledge. Yeah, exactly.
Right.
Exactly. And domain adapted adaptive pre-training gives us a way to let the model learn this topic, from the roots, where something like fine-tuning doesn't work as well. You might think to yourself, well, models aren't trained on knowledge of cheese, they're trained on knowledge of everything. Well, they're not really trained on knowledge of everything, right? They're trained on internet corpuses for the most part, and book corpuses for the most part, which, while aren't as obviously distinct from law as just knowing a lot about cheese. In practice, are pretty distinct from the language and its use in law. And that's one specific and
Yeah,
easily
so
understood.
if we stick with the cheese and law
Yeah,
idea here, okay, and Martin has a great point here in the chat. It's like
yeah,
one thing I could do is I could take a model off the shelf and I could fine tune the cheese model. Let's call it fromage.
yeah.
Fine tune the legal easy model, and then I could boom merge them just like we did with the Riddler.
That's
And
right.
and that would be one solution. You're saying like another solution could be do some pre-training, do some additional pre-training towards cheese, you know, and some additional pre-training towards law, something like that.
In this case, I'm more saying like even off the shelf models, which are trained on internet corpus data for the most part, in books often, uh, aren't good at law. So, and there, no amount of SFT is going to make them better at law past a certain threshold, right? And so this idea that we need them to learn the root of language in law, which is just a great example because language is super specific and different in legal domains, right? So it's like we can't just nudge them towards law, right? We've got to really from the bottom up teach them. And this is you could merge different models together if you had, say, a model that was pre-trained on legal data that already had DAPT applied, right? You could merge that into your generalist model, and it should most definitely get better at law tasks. Um,
Mm.
but the idea is that some language is so distinct that SFT is too superficial to really get a deep understanding of these phrases. We can't just show it many examples, right? We have to kind of let it read through all of the textbooks, all of the legal reports, all of
Mm.
the legalese to build those
Yeah,
strong
yeah.
connections.
Because it's fine tuning, right?
That's right.
It's not training,
That's right.
right? And
That's
we
right.
talked about this, you know, we talked about this maybe for at least a year now, sort of understanding, sort of standing under the law and sort of being able to sort of really grok the entirety of it is sort of what you get out of a pre-training process versus what you get out of a fine-tuning process is just sort of maybe top down, sort of dialing in, you know, again, accessing where prompting won't really allow you to in a more constrained way. And so you're not really building out the corpus fundamentally of understanding. You're building out more of this rewired, constrained version of the model.
That's right.
So, but you
The
need
language
GPUs
is
for this.
fundamentally different. It's not just superficially different. It's not a fine difference between law and regular English or like Reddit, right? It's fundamentally the usage of language is fundamentally different,
Mm.
and you need a lot of GPUs to answer the
You need
question. You
lots of
need
GPUs for
so
this,
many
basically.
GPUs.
Yeah, yeah, yeah,
Yes,
yeah, yeah,
yeah,
yeah, yeah.
absolutely, yes, yeah,
Okay, okay. So
just
in the end,
tons.
maybe that's the big takeaway, right? You want to do continued pre-training, you better have them GPUs. Okay, so I want to end on this before we go to our fun time here, everybody. And let's let Wiz, I want to keep you up here because we had a discussion with the Distill Kit with the Distill Kit folks and the Arcee folks, and we were talking with two guys that just got their PhDs, literally just got their PhDs. They started working for Arcee. They worked on the right thing at the right time to be in the right place for SLMs, right? And we talked to them about what's the way, knowing everything you know now, you would learn the sequence in which you would learn this kind of stuff. And this is what we came up with. It was supervised fine tuning, DPO, merging, then distillation, then continued pre-training. And I kind of have these not bolded because they were kind of like, meh, you know, do you really need these? Because you're starting to get into this heavy GPU category when you get into these, right? These are going to get you really far. And this, I think, you know, when we talk about LLM engineering and the jobs that are going to exist and the small language models and the hundreds and thousands of models at each company's, you know, these are the kinds of things that you're typically going to be leveraging much more than these kinds of things. You know, knowing a little bit about all of them, probably super important. But knowing a lot maybe about these three, probably more important, is my big takeaway. What's yours?
Yeah, I mean, you should just straight up like not learn 4 and 5. It's a waste of your time unless it's not. Like if you're working for the biggest companies in the world that have the most GPUs, it's a little bit of a different story, but very few people work in those environments, right? And the people who do likely already have a very well established connection to the first 3 bullet points. So yeah, like learn the things that are in bold, and if for fun you want to dive more into distillation, if for fun you really want to understand continued pre-training, you'll be an asset in some way to your company because it's going to build a fuller image of machine learning and how we interact with train and use LLMs. But you're not going to use that practice, right? So I would say unless you are already you feel like you have relative expertise in the first 3, you just won't be in a situation where you're going to be in the resource requirements for 4 and 5, right? If we look at these paths as like L's, right? This is like an L6, 7 thing for 4 and 5 in kind of tech. So if you're at that level, yeah, for sure, learn it and work for the big companies with big GPU farm, right? But otherwise, you know, do the stuff that's useful to all businesses as opposed to only like 4 of them.
And then nerd out on distillation and continue pre-training in the community at AI Makerspace with us. Yeah, do that. Because we're all post-compute here. Maybe we'll be able to do it when, you know, the compute gets better and the cost comes down and all that. Okay. Thank you, Wiz.
Here is our trivia game, and here are our wonderful categories. Transformers and attention. Okay, what 2 regularization methods does the traditional transformer network use? Let's find out. Residuals, dropout, alignment for 300. All right, here we go. What are we aligning to? So the correct answer was human preference. All right. Training and fine tuning. 300. Everyone just wants to just get some points. Okay. What is batching? Is it moving batches of information through the network at a single time to take advantage of parallelization? Is it to reduce the total numbers of samples processed during training? Is it to simplify back propagation by using a single sample? Or is it to ensure the model updates weights after every sample? What do you all think it is? All right, the correct answer is A.
Can we do training and fine tuning for 400?
What kind of loss do we use during training? All right, let you guys know the answer. It's cross entropy. Woo! 400, alignment for 400. What is the major advantage of DPO over RLHF? What is it? You guys got 4 possible answers. Is it that it eliminates the need for any online reward modeling? What's the major advantage? Maybe RLHF requires larger data sets. Maybe it's C, no translation to RL domain. Or D, it provides deterministic outputs instead of probabilistic ones.
I like this one. This is a good one. Yeah, this
You
one's
like this
solid.
one?
This
All
feels like a
right.
whiz special right here. That's what this one feels like.
All right, here we go. No translations to RL domain.
Transformers and attention for 400.
What operation happens in the highest volume in a traditional transformer network?
Matrix multiplication.
Nailed it. Nailed it. Good job. Matrix multiplication.
Training and fine-tuning 200.
What is the difference between SFT and training? So yes, it's supervised versus unsupervised learning.
Let's go for alignment 200.
Is PPO gradient descent or gradient ascent?
Let's go hardcore with transformer attention 500.
Yes, I like it. Let's just go there. All right. Where do we apply ROPE? It's multiple choice for you. Is it normalization, embedding layer, action layer, or softmax? Was that obvious? Was it not obvious?
Whiz.
Rope is an embedding strategy, but we apply it during the attention mechanism. Yes, I know. It's intentionally tricky.
Transformers for 200. Here we go. What is attention's time complexity?
And just in case you're not a Python head, the star means to the power of. So the first one is n to the power of 2, and then the fourth one is 2 to the power of n. N will represent sequence size.
Close it now. Let's see what the correct answer was. It was B.
Training and fine-tuning 500.
What is the Karpathy constant?
Can
You've
we have
got-
that one more time? One more time?
Karpathy.
What's the name?
What is the answer? It is B.
Well, I mean, it's got to be alignment for 500. Let's go.
Why do we need to use methods like DPO and PPO instead of using full SFT for alignment? This is multiple choice. It's B, avoiding overtraining small nudges. Attention for 100. Let's do it. What operation converts logits into a usable probability distribution? All right, let's see what the answer was. Softmax! Woo woo! What does GPT stand for?
What a classic. What an
I know.
absolute classic.
Generative pre-trained transformer.
And with that, we're going to go ahead and talk a little bit about frontiers here. And so as we get into the frontier space, like we can kind of understand everything from first principles now. We talked earlier about Spectrum. Spectrum is the fine-tuning solution from Arcee. And Spectrum is basically trying to say, hey, I'm trying to actually optimize not just the fine tuning, but actually the training of LLMs, because this is an emerging space where people are interested in training not just on single GPUs, but across many GPUs. You probably heard of Elon's Colossus. You probably heard of the way that we're trying to train these types of systems. And really, you have to do this in a very smart way because GPUs, they will go down. You have to make sure that you're sort of shuffling memory properly. You have to make sure you're doing your attention calculations in a way that's not going to totally mess up training or fine-tuning of these very, very large models. So this is the context in which we see something like Spectrum come onto the scene. Efficient post-training. This is a big thing, efficient post-training. And so like when we try to get this sort of more efficient memory usage and shuffling, this is a very, very key concept that as you get into building, shipping, and sharing production LLM applications, you'll see more and more of. Whether it's flash attention, whether we're dealing with quantization, whether we're looking at some of the serving techniques and micro optimizations, all of this stuff adds up to being more efficient with the on GPU memory. And that's no different here. Now, this has a kind of a cool approach that I'll leave for you guys to sort of read further. It's called the signal to noise ratio that they're kind of looking at throughout the layers here. But in the end, this is trying to kind of reduce training time, be more memory efficient, and as we hear with many, many things that people put out, kind of reduce catastrophic forgetting. This could be said of merging as well. And so this sort of approach that they have, and we did an event on this, so I'd encourage you guys to go check it out, randomized matrix theory and Marchenko-Pastor distribution. But basically, we're looking at layer signal to noise ratios in each layer. And that's going to basically help us choose which layer is providing the most signal to noise. That's the one I should train. This is the big idea. So you do that SNR analysis, you select the layers, then you target the training. Wiz, is Spectrum something that's different enough from like a LoRa that's popular enough that people should know about it, know how to use it now, or not so much?
I would say not so much right now. There's perhaps the potential that this changes, but for right now, the kind of scale that we want to be thinking about, LoRa and Spectrum are just not well aligned. We also have a lot of optimizations that we've made to LoRa over the years. Spectrum definitely, as we progress forward, as more and more companies wind up with more and more GPUs, might indeed, be the long-term plan. But for right now, sticking with LoRa is absolutely not gonna be a bad idea. And then as we again, get more ready access to more and more hardware, things like Spectrum, we're gonna start making a dent. Absolutely, yes.
LoRa does learn less and forget less, as we saw earlier, right? So pretty good at catastrophic forgetting already, let's say. Okay, there's another thing that I want to move to quickly here, which is sort of in this emerging space of transformer architectures. There's a lot of stuff happening, but really the one that is probably most useful to take a look at while we're still together in this class today is the mixture of experts. And the big idea is the same exact idea that we heard from Jeff Hinton in his paper when this was kind of coming onto the scene, the original distillation, right? It's like it's not a mixture of experts approach. This idea of mixture of experts and getting sort of the wisdom of the crowd computationally is not sort of a new intuitive idea. It's just something that people are applying everywhere. So I want to just show the diagram here, and Wiz, I'd like to bring you back up for this. Really, it's not that different than a transformer. We're zoomed in here all the way in to a single block, a sort of decoder block. So you guys will feel very comfortable here with the self-attention, add and norm, then the feed forward network, then another add and norm, and then we're moving out of this block. What's going on here, Wiz, with this switching FFN layer? Why is this a powerful pattern? And what are some of the implications for, let's say, efficiency and training? Muted.
Oh, what we can look at for MOE most specifically is this idea that we kind of have this intuition or idea, right, when we're working with something like our dense network, that there's this attention heads, right, develop some amount of quote unquote expertise at attending to certain kinds of things, etc. Right? This is basically MOE made this like more for real. So this switching allows different networks to be responsible for certain kinds of things in the network, right? And then instead of having to go through the whole network, they can just go through the parts they need. So the whole network is bigger, but the inference path is actually the same or smaller. So like, popular versions like 7B, right? So many different 7B experts. Well, what we can do is every time we run inference, we're only going through 7 billion-ish parameters versus needing to go through like 7 times 8 billion parameters, right? Which is like too many parameters. So this is the idea. It gives us this optimal route for certain tokens to go through. MOE confers a lot of different advantages. It is more capacity that is required, so you need more GPUs to host this thing, but the inference is very fast. As for speeding up training, it doesn't speed up training relative to a single network that's the size of an expert, but it does absolutely speed up training compared to an equivalently sized large language model. So if we have like 7 times 8, right, that's going to be faster than, you know, just one big network that's got got so many parameters. The basic idea though is just encoding into the architecture this idea that certain tokens should take certain paths through the network, and we should become experts at those particular kinds of relationships. We see experts like punctuation experts, article experts, so the a things like
Fromage
that.
experts,
Cheese
law
experts,
experts.
absolutely,
Yeah.
yes,
Right.
yes.
Right. Yeah, but there's one key thing here, which is like you have to hold all of this in GPU RAM to be able to do inference, right? So that's kind of one of the drawbacks and one of the difficulties when we get into fine tuning of these. And so they are useful. They are kind of good at some things, you know, relative to a model of the same size in 7B, that's sort of the traditional dense version of the transformer. But you know, we're not seeing huge application out there in industry for this kind of thing. Are you staying tuned for that? Do you expect it?
Absolutely. I mean, our everyone's favorite model is most likely an MOE model, right? So this is ChatGPT. If you use ChatGPT 4.0, it's all but confirmed by OpenAI to be an MOE. I think these kinds of networks are just really good at what we want them to be good at, which is being really powerful generalists that are easily run when we have big boy networks or big boy hardware that we can support the additional overhead of needing to hold lots of model and memory at a time. It does, the training is basically the same as normal transformers, same kind of paradigm, very small differences. The training is also hella unstable, which means that you know, having really good infrastructure for starting, restarting, checkpointing is going to be more important for MOEs as well. We have to do some fun tricks when we're doing the pre-training process to kind of make sure that this particular model doesn't go off the rails.
Yeah. And you said something there that I just want to, like, you know, make sure people heard. Like, you said that it's all but confirmed. This is actually that ChatGPT is a mixture of experts model. So, you know, this is from the State of AI report 2023. This was October 2023 that people were saying this. So this is an important thing to pay attention to. Obviously, it's closed source. We don't know for sure. But this is sort of the, well, there's a great meme here. And then, you know, this sort of performance increases that they're seeing sort of indicate to a lot of experts that, hey, maybe this is an MOE. So stay tuned for MOEs. This is one of the ones we wanted to make sure that we covered. Okay, and finally, I want to talk about reasoning. This is the very last thing. And so, you know, we've talked a lot about this O1 model came out. And it says a new large language model. This came out September. So this came out, like, you know, not long before we started this course. A new large language model trained with reinforcement learning to perform complex reasoning. O1 thinks before it answers. It can produce a long internal chain of thought before responding to the user. And check this out. It exceeds human PhD level accuracy on benchmarks of physics, biology, and chemistry problems. The graduate Google proof QA one. Remember the one that Supernova didn't do so well on? O1's like, yep, got you. And what is happening here, and that's so interesting, sort of out at this edge, is, you know, the performance of O1 consistently improves with more reinforcement learning, train time compute, and with more time spent thinking, test time compute. Watch these words. These are going to become more and more popular. The constraints on scaling this approach differ substantially from those of LLM pre-training, and we are continuing to investigate them. So just a quick background, you know, when we use language models, we typically are telling them, hey, think through this step by step, especially when we give them a math problem. This is the idea from the Chain of Thought paper 2022 from Google, where, you know, it's literally just better if you tell it to think through. This is the classic example of, you know, a student in class, you know, Tommy basically says, oh, the answer's 11. And you're like, Tommy, bro, how'd you get that? My guy, like, you're not even trying, right? Where it's like, then you call on Susie and you're like, Susie, how'd you get your answer? And Susie's like, well, we had 23 apples over here. And if we use 20 and then bought 6 more, and it's like, if you think it through, that student is going to do better than that student. It's the same with LLMs. And it's the same with giving instructions to humans as with models, as we sort of have continued to see throughout this course. And there's also this idea that LLMs can assess their own thinking. So you basically tell it to, hey, I like that answer, but I need you to go and check it again. This is the idea of self-refinement, of reflection. I'm going to go ahead and not talk about self-refinement and reflection in the interest of time today. What I'd like to do instead is I'd like to sort of just Wiz, if you could give us a quick whiz runaround of the O1 model. We saw 3 R's in strawberry to start off this course. And, I want to really try to understand, like, where are we headed here with this sort of reasoning? Is this like agentic? What's going on here? It's like there's all sorts of interesting things happening out at the LLM Engineering Edge. So I want to hand it off to you to do one final demo before we kind of close it out for our little graduation ceremony. Wiz?
Yeah, I mean, basically, it takes time to think. It sounds glib, and it kind of is glib, but that's what it do. You'll notice that it has these kinds of thoughts, right? So we're just gonna see if it can crack the Enigma code for us real quick, which it may or may not be able to do. But the idea is that you can see here that we're thinking, right? We're thinking about the everything. Now we're getting the final output here, right? So the idea is that this is just a really, really, really good model at this part, okay? So this part's dope, and we get this whole thing. It could be a code or a cipher key. It could be a step in a puzzle. They can't actually decode it without any additional information. That's okay. It took a lot of scientists a really long time to do this, though sometimes it will crack this code. The idea is that it's really good at this thing. And this doesn't seem like a lot, right? And to be clear, this is a summarization of what it's actually doing here. The big idea behind this is that it just takes more time to think, as in it produces way more output, right? So instead of just going right to the answer, it's going to produce many tokens in a row that are all to do with this, this particular thing, deciphering the code, trying to decipher the code, piecing together clues. Again, it fails on the task, but it gets really close. It gets way closer than, something like ChatGPT would get, which might not even notice that this is a cipher, right? It might not even get that this is a puzzle that it should be trying to crack. And you can see here, what they did, right, is we know RLHF, right? We have familiarity with that. So they used RL minus the HF, and that's okay, to get the model to be really good at this part, this thinking part, right? This piece is just normal. This is just like all LLMs do this part, right? This is the part that's novel. This is the part that's new. And what they did essentially is every time the LLM has a good thought, they reward it. When the LLM have a bad thought, they don't reward it. And they kept doing that over and over again until they eventually got to the result that we see today, right? What we can take from this is that the LLM can get to the right answer, assuming it can just spit out enough stuff to allow it to get the correct formulation of things in its context, right? And that's due to the fact that these are autoregressive systems. They look at their own outputs, right? So if it gets very good at producing outputs that will be useful for it to look at later, then we can see the kind of direct line to this thing being more reasonable. this is the this is kind of like the insight, and that's what they did, and that's all that they did. And I want to take a moment just to, again, it tried its best. Okay, it didn't win. That's okay. But you know, what we're happy about here is the fact that it thought through every possibility, right? And all we did is we told it, hey, think more, right? So this is 2024, and we've told the model to think more, right? That's the elegance with which we're approaching this. So the future is very bright for these strategies. We don't even know where to begin. A lot of NeurIPS was focused on that this is going to be the next NeurIPS, right? So 2025 is going to be a lot of research about exactly what you see here, which is this idea of thinking through the problem, thinking more. Humans think more. I think more. Greg thinks more. And we can do meme stuff, you know what I mean? Like, we can ask it fun questions. Obviously, with the strawberry one, you know, we could do things like prove the theory of relativity. You know what I mean? And then we can watch its thoughts. It doesn't even need to think. It just starts doing it. Okay, that's good. Good for it, right? You can give it mathematical proofs where it has to construct them whole cloth. It's great at that. There's almost nothing this benchmark is able to do. There you go. I don't know. 01. It's insane. It's the most powerful model that we have, and all it does, again, right? We'll ask it another one. Like any question. Who's got a good question? You know what I mean? Who's got a question that they think it can't answer, and we can
Who's
see.
got one? Who's got one? Let's go.
Okay, what is Yaldanite?
What is the
Yalda, YALDA, then night. Night.
night?
Yes.
I don't know the answer to this question. This is perfect. It's thinking. It's a celebration. You didn't need to think a lot. Kind of knew that, right?
Too
It's
easy. Too easy.
It's still good at regurgitating knowledge. Who's got an even harder question? Any math peeps in here? What do you wish you saw proven in front of your eyes by a language model?
Can you produce a transformer that uses Clifford algebra instead of standard linear algebra?
Transformer.
AI
I
model.
put the architecture that uses Clifford algebra
instead of standard contemporary linear algebra.
I think it's gonna know that. In PyTorch. I think this one's good. It might have to think a little bit longer. Integrating Clifford algebra, charting the course, creating the blueprint, clarifying Clifford multiplication, refining the approach, mapping token embeddings. All right, I don't know anything about this, so it's up to you to determine if this is correct or not. But this is the part it's good at, right? Like this is
a reason about it. At least it's pretty good.
Yeah, and this is all the model is doing, right? It seems so easy. It's just thinking more. It's just plopping more tokens down, right? And that's where we're at in 2025. That's where we're at.
Plopping more tokens. Let's go.
Let's go.
Who wins?
Okay, there you go.
Congratulations. You just finished LLM Engineering, Foundations to SLMs. You've explored the transformer, attention, embeddings, next token prediction, unsupervised pre-training, supervised fine-tuning, alignment, distillation, model merging, and more. Covered so much ground, all from first principles, from concepts to code. So now what? The future of small and large businesses alike will be agentic. I'm sure you've heard. But these agents, they're just LLMs. They're just highly specialized LLMs, often with access to tools. You might say that they'll be right-sized, small language models, or SLMs. Now you have the knowledge to pull models off the shelf, to customize them. Models will improve, but the importance of being able to take commercial off-the-shelf tools and adapt them to your use case while using best practice LLM engineering techniques isn't going anywhere. While experts like Andrej Karpathy and others agree there will be more AI engineers than LLM engineers, it will continue to be important to understand what's really going on inside of our language models. As you build at higher and higher levels of abstraction, and the software engineering stack you use continues to advance in the weeks and months and years to come, understanding these foundations will continue to be important. Really, all that's left is for you to figure out what you should build and why. Better, what you should build, ship, and share, and who you should share it with to create real value for yourself, for your family, for your community, for your company, and for the world. We look forward to following your journey from here. At AI Makerspace, we are on a mission to create the world's leading community for people who want to build, ship, and share production LLM applications. Congratulations again. I invite you to join us at AI Makerspace to help us accomplish our mission. I challenge you to keep learning, keep building, and keep sharing at the LLM Edge. Until next time, we'll keep building, shipping, and sharing, and I hope to see you do the same.